You're sitting still right now, reading this, not moving. But what does not moving mean? Not moving relative to what? Your chair, the ground. Is the ground moving? How would you know? We say stationary means not moving, but that's just saying the same thing twice. Not moving compared to what? The answer isn't about what motion is. It's about what we can actually measure, and what we discover changes everything about up, down, and whether the earth beneath you is. You'd say, stationary means staying in one place. Simple enough. But watch what happens when you try to actually measure it. You need a reference point, something to compare against. Your chair, that's also on the ground. The ground, well, that's what we're questioning. Already we're going in circles. Galileo figured this out with a thought experiment. Actually, more than a thought experiment. A real observation you could make below deck on a smooth sailing ship. Drop a ball. It falls straight down to your feet. Toss it to a friend across the cabin. Same arc as if you were on land. Butterflies fly around normally. Pour water from a bottle. It drips straight down. Fish swim in their bowl just like they would on shore. Everything behaves exactly as if the ship were sitting still at the dock, but the ship is moving. You can go up on deck and see the shore sliding past. You're traveling, say, 10 miles per hour relative to the land. Below deck, no experiment you can do reveals that motion. Not one. Drop the ball, toss coins, jump straight up. You land in the same spot. The motion is completely invisible to any mechanical test you could perform inside that cabin. This was the realization. Motion and rest are indistinguishable by any mechanical experiment, not philosophy, actual observation. You cannot tell from inside a smoothly moving system whether you're moving or stationary. There's no test that reveals the difference, which raises an uncomfortable question. What about the earth? The Aristotelians, the scholars who followed Aristotle's ancient physics, said the earth must be standing still. They had what seemed like solid proof. Drop a stone from the top of a tower. It lands at the base of the tower, directly below where you released it. If the earth were moving during the time the stone falls, they argued, the tower would move sideways while the stone is in the air. The stone should land behind the tower, in the direction opposite Earth's motion, but it doesn't. It lands right at the base. Therefore, Earth must be stationary. Seems logical. Wrong. The stone shares the Earth's motion before you drop it. It's already moving sideways, at the same speed as the tower, the ground, you. When you release it, it keeps that sideways motion. It doesn't just fall down. It falls down while continuing to move sideways with the Earth. So it falls straight down, relative to the moving Earth and the moving tower. Just like dropping a ball on the ship. But people resisted this explanation deeply. Common sense says you should feel motion. We feel bumps when riding in a carriage. We feel turbulence on a plane. So if Earth is spinning, shouldn't we feel it? Here's the thing, those bumps and turbulence are changes in motion, accelerations. The carriage hits a rock, your speed changes suddenly. The plane hits an air pocket, direction shifts. What you feel is the change, not the motion itself. Constant, smooth motion, nothing to feel. No mechanical experiment can detect it. This is what bothered people. If the Earth moves, they asked, shouldn't there be a constant wind from our own motion through the air? Shouldn't the air get left behind as Earth spins beneath it? Actually, no. The air moves with the Earth, just like the air inside the ship's cabin moves with the ship. Everything, ground, buildings, oceans, atmosphere, moves together. There's no relative motion between you and the air around you to create wind, no relative motion to detect. Here's what this means, and it's disturbing when you really think about it. Stationary is meaningless as an absolute term. You can only be stationary relative to something else. Choose a different reference, and suddenly you're moving. Sitting in your chair right now, you're stationary relative to the room. But the room is on Earth, so you're moving about 1,000 miles per hour at the equator. That's Earth's rotation. Earth is orbiting the Sun at roughly 67,000 miles per hour. The Sun is orbiting the center of our galaxy at something like 514,000 miles per hour. And the galaxy itself is moving through space at over 1,000,000 miles per hour relative to the cosmic microwave background. All of these statements are simultaneously true. You are stationary. You are moving 1,000 miles per hour. You are moving 1,000,000 miles per hour. Which one is really true? Which reference frame is correct? None of them, or all of them. There's no or preferred reference frame, no cosmic measuring stick that says this is truly at rest and everything else is moving relative to it. Let me show you this is real, not just philosophical wordplay. Fire a cannonball due north from the equator. Watch what happens. It deflects east as it flies. Not because some mysterious force pushes it east, because you fired it from a rotating Earth. At the equator, you and the cannon are moving east at about 1,000 miles per hour, Earth's rotation carrying you around. Farther north, the Earth's surface moves slower because it's tracing a smaller circle. Same rotation rate, smaller circle, lower speed. The cannonball, when fired, keeps its original eastward speed from the equator. So as it travels north over ground that's moving east more slowly, it appears to curve east. It lands east of where you aimed. This is the Coriolis effect. We can calculate exactly how much deflection there should be based on Earth's rotation rate and the cannonball's flight path. Then we measure the actual deflection. They match precisely. This proves the Earth rotates, not by feeling the rotation directly, but by observing its effects. We're moving but smoothly, so we can't feel it, but we can measure the consequences. Same principle with Foucault's pendulum, demonstrated in 1851. Hang a heavy pendulum from a very long wire, set it swinging in one direction. Over the course of hours, the plane of the swing appears to rotate. Clockwise in the northern hemisphere, counterclockwise in the southern, but the pendulum's swing plane isn't actually rotating. It's staying fixed in space. The Earth is rotating beneath it. As the floor turns under the pendulum, from our perspective on that rotating floor, the swing direction seems to change. At the North Pole, the swing plane would complete a full rotation in 24 hours. One full Earth rotation. At the equator, there's no apparent rotation at all, because the pendulum is moving with the Earth's rotation there. We can predict the rotation rate at any latitude based on Earth's rotation. We measure it. Perfect match. Visible proof of motion we cannot directly feel. The pendulum stays still, the Earth moves. Now you might ask, but surely there's some absolute reference, space itself, some cosmic background? The physicists of the 19th century thought so. They believed in something called the luminiferous ether, a substance that supposedly filled all of space and served as the medium through which light waves traveled, the way sound travels through air. If the ether existed, we could measure our absolute motion through it. Picture it. We're on Earth, moving through this ether as we orbit the sun. Light traveling in the direction of Earth's motion would move through the ether differently than light traveling perpendicular to our motion. Like swimming with or against a current versus swimming across it, different speeds in different directions. Albert Michelson and Edward Morley decided to test this in 1887. They built an extraordinarily precise instrument, an interferometer, that could detect tiny differences in the speed of light traveling in perpendicular directions. They sent light beams in different directions and compared how long each took to make the same journey. They measured, very precisely, the most careful measurement that had been done up to that time. No difference. Light traveled at exactly the same speed in all directions, regardless of Earth's motion through space. They repeated the experiment. Same result. Other scientists repeated it. Same result every time. No matter how Earth moved, whether in January or July, morning or evening, different orientations, light always traveled at the same speed in all directions. The ether doesn't exist, or more precisely, there's no medium that defines a state of absolute rest. Even light can't give us an absolute reference frame. This result bothered everyone so profoundly that they kept repeating the experiment for decades, trying to find some flaw. But the answer was always the same. Eventually, this null result forced Einstein to develop special relativity. The speed of light is constant in all reference frames, and there is no absolute space or absolute rest, but that's a different story entirely. Go back to what Galileo actually observed. On the ship, below deck, no experiment reveals motion. On Earth's surface, no experiment reveals the rotation. Why? Because smooth, constant motion has no mechanical effects. Only acceleration does. Changes in motion, changes in speed or direction. You feel the carriage bump when it hits a rock. That's acceleration. You feel the airplane bank into a turn. That's acceleration, change of direction. You feel the elevator lurch when it starts moving. Acceleration again. Constant velocity at a steady speed in a straight line. Nothing. No physical sensation. No mechanical effect. This is Galileo's principle of relativity, stated in 1632 in his dialogue concerning the two chief world systems. The laws of motion are the same in all uniformly moving reference frames. It doesn't matter whether you call yourself moving or stationary. The physics works the same way. Drop a ball, same result. Throw something, same arc. Fire a cannonball, same trajectory. The most radical claim, the Earth could be moving, spinning on its axis, orbiting the sun, and we would never feel it. Not because the motion is too slow or too subtle, because uniform motion has nothing to feel. It produces no effects that distinguish it from rest. What do we actually see when we do experiments? We see that dropped objects fall straight down relative to us. We see that projectiles follow the same paths, whether fired east or west. We see that the physics in our laboratories works the same way all year round as Earth orbits the sun. All these observations are consistent with either Earth being stationary or Earth moving uniformly. The experiments don't distinguish. Only when we look for the subtle effects of Earth's rotation, the Coriolis deflection, the Foucault pendulum, do we find evidence of motion. And even then, it's not the motion we're detecting. It's the rotation, which is a kind of acceleration. So return to the original question. You, sitting in your chair. Are you stationary relative to the chair? Yes. Relative to the room? Yes. Relative to Earth's center? No. You're rotating around it once every 24 hours. Relative to the sun? Definitely not. You're orbiting at tremendous speed. Relative to distant galaxies, you're moving very fast in multiple simultaneous directions. Relative to the cosmic microwave background radiation, you're still moving. All of these are equally valid descriptions. No one is more correct than the others. No reference frame is privileged or special. Stationary only means not moving relative to this specific thing I've chosen to measure against. It's not a property of the object. It's a relationship between two objects. This is what Galileo discovered that disturbed everyone in the 17th century. Motion isn't absolute. Rest isn't absolute. They're relative terms. They always were. We just didn't realize it. Why didn't we realize? Because we're stuck on Earth's surface. Everything around us, the ground, buildings, trees, other people, the air, shares our motion. They're all at rest relative to us. This creates a powerful illusion of absolute rest. We look around and see stillness because everything moves together. It takes getting on a ship or thinking carefully about a rotating planet to reveal the truth. Motion is only meaningful relative to something else. There's no absolute motion, no absolute rest. This realization didn't just change physics, it changed philosophy. If there's no absolute reference frame for position and motion, maybe there's no absolute reference frame for other things either. Maybe up and down aren't absolute directions, but just labels for toward Earth's center and away from Earth's center. Maybe a lot of things we think are absolute properties of the universe are really just relationships, things that depend on perspective. And here's what keeps me up at night, what I think about when I look at the stars. If motion is relative, what about acceleration? We can feel acceleration. It seems absolute. Drop from a tower, you feel yourself falling. Stand on the ground, you feel solid and still. There's a clear physical difference. But wait, Einstein asked this exact question 3 centuries after Galileo. What's the difference between falling and standing still? When you're in free fall, truly falling, nothing touching you, you feel weightless. No force on your body. You're following a natural path through curved space-time. When you're standing on the ground, you feel your weight. The ground is pushing up on your feet. You're being accelerated. Standing on the ground is constant acceleration upward. Free fall is the natural, unaccelerated state. Gravity isn't a force pulling you down. It's the curvature of space-time, and standing still means constantly accelerating to resist that curvature, which means even acceleration depends on your perspective. What feels like acceleration in one frame is natural motion in another. The person falling and the person standing still disagree about who is accelerating. And the mathematics of general relativity says they're both right. But that takes us from Galileo to Einstein, from the relativity of motion to the relativity of space-time itself. Different story entirely, different century, different physics, different way of thinking about reality. For now, for what Galileo showed us. Next time you sit still, reading or working or thinking, remember this. You're moving at 1,000,000 miles per hour through space. And you're staying perfectly stationary. Both statements are true. Both are false. It depends entirely on what you choose to measure against. There's no cosmic answer sheet saying which description is the real one. Eppure si muove, and yet it moves. That's what Galileo supposedly muttered after being forced to recant his claim that Earth moves. The Earth does move, and it doesn't. You do move, and you don't. The question, are you moving, has no absolute answer. It has many answers, all equally valid, depending on your reference frame. What can we actually measure? That's always the right question, not what is really true, but what do our instruments show? We can measure that you're at rest relative to your chair. We can measure that you're moving relative to the sun. We can measure the Coriolis effect that proves Earth rotates. We can measure the constant speed of light that proves there's no absolute rest frame. All these measurements are real. All these descriptions are accurate. Motion is relative, always was, always will be, and that leads to the next question, the one that haunted Einstein. If motion is relative, what about time? Does time flow at the same rate in all reference frames or? But I've got to stop somewhere.